Okay. Well, it's great to be here. I'd like to thank all the organizers, the wonderful hospitality of everybody who's working here. Couldn't be more wonderful. This is a part of a distinguished visitor lecture, and there are, of course, a number of distinguished visitors in the audience, and the younger people will become distinguished. So it's really wonderful to give this lecture. The title of the lecture is the Constraint Search, Formulation and Coordinate Scaling Properties, or Constraints in Density and Density Matrix Functional Theories, with the emphasis on density functional theory, and I'll say a little later more about some density matrix functional theory. Now, this is what I'm going to talk about. First, of course, we have the motivation for density functional theory and density matrix functional theory. The wave function is very complex. Dirac had said that you really can't get any much useful information. It's just too big. So I'll go through the brief early history of density functional theory. On Tuesday, I'll talk about the personalities involved in some stories more. This will be more brief. It started with the Holmberg-Kohn functional that defined precisely what Thomas Fermi was trying to approximate. Then I'll go into the Levy or Levy-Leib constraint search. From all these three, you get constraints, and I'm going to emphasize coordinate scaling constraints for helping to develop approximate functionals and understand their structure. Understanding the structure for even beginning students comes very, very easily from the use of coordinate scaling. Then there is a difficulty inspired by the work from Karen Burke's group years ago. There was a problem if you're just scaling one of the spin densities. How do you get how the properties of the functional change, and how do you use the scaling? Could you derive coordinate scaling constraints or properties? And this is difficult because you're scaling just one of the spin densities, but in your wave function that contains spin, the whole wave function is antisymmetric. So this is a tough thing to do, and I think we figured out how to do this. We have Federico Zaharia and I, a former postdoc, a former graduate student of mine and a postdoc of Karen, now at Iowa State. We figured it out by using spin-free wave functions. So then I will go through spin density functional theory through the use of spin-free wave functions. So that will be the latter part of the talk. Okay, so obviously this is our problem here. The Schrodinger equation, difficult, as we all know. It's one of the reasons we're all here, is that it's a complicated problem, 3n dimensional. Schrodinger in the middle 1920s, 3n dimensional, difficult. So we then have the electron density, and has only 3 dimensions. So if you know the functional, you could use the electron density and We have wonderful approximations now, and they're getting better. The meaning of the electron density was not put forth by Schrodinger. Schrodinger did not understand that, or did not believe that psi squared dx in the region between x1 and x2 is the probability of finding the electron there. It was not understood, and he fought it, Schrodinger. The person who put that forth was Max Born. And Max Born won the Nobel Prize for that. That's what he won the Nobel Prize for. So when you start getting into a field early, you could do profound, if you make a profound observation, it could go very far. A very interesting point there. Born had done many things, but he won the Nobel Prize for this. Then, of course, we have the Thomas Fermi theory that was talked about earlier in the tutorial lecture by Heinz Seidentop. That came first right after the Schrodinger equation, and it has the correct kinetic energy for a uniform electron gas. Okay, so in a sense, it's the first LDA, or local density approximation, before the kinetic, and this approximates the repulsion. And then there was a lot of follow-up work, and Heinz talked about it. Very interesting follow-up work, but this was what Holmberg-Kohn did that caused the revolution. Okay, you start using densities because the wave function is too complicated, right? That's why you use the densities to avoid the wave function. But then what they did is, let's see if we could use the wave function to define what Thomas and Fermi is trying to approximate. So that caused the revolution. Now, the revolution, you could say, was caused by the theorem. But I think it was caused more by the question. Once you say, can you prove that you could define a universal functional of the density so that when you do the minimization, the energy minimization by varying the density, you get the exact energy. Once you do this, and you give it to a bunch of good graduate students and postdocs and give them a week, I think we'll come out with the answer. And I think also the version that people will come out with is the constraint search version, and not the original proof by contradiction that Holmberg and Kohn did. They said you use proof by contradiction that says a ground state density cannot belong to more than one external potential, and then you get it that way. That's the way they did it. And then you have a restricted class of densities that are used in their functional as a result. But since you were saying we have a variational problem, I think it's quick to just go right down the variational theorem, right down, and do it. I thought if you give it to a large number of people, that question, I think many more people would come out with the constraint search version than with the original proof by contradiction by the Holmberg-Kohn. Okay, so we have Thomas and Fermi, and then I said, Hohenberg and Kohn asked, what is Thomas and Fermi trying to approximate? And you see, they entitled the paper "The Inhomogeneous Electron Gas," knowing that Thomas Fermi kinetic is exact for homogeneous electron gas. Inhomogeneous electron gas. Thomas was Hohenberg was a young postdoctoral in Paris, and Kohn was on sabbatical from the University of California in San Diego. And they met up in Paris near the Luxembourg Gardens. That is, Kohn told me, is his favorite spot in the world, I guess, because he remembered doing the work there, and he loves to go there. And then they worked on this problem. But you see, because of the way they did it, with the F Hohenberg-Kohn functional is you have psi yields rho, where psi is the trial psi here, trial psi, that gives an arbitrary rho, is the non-degenerate ground state of some external potential V prime, not necessarily the one, of course, that you're interested in. Only if it's the ground state you will get that. And this is a restricted class. They came from their original proof. Now, Elliott Lieb and I, in 1982, showed that there's a large class of densities which are not non-degenerate ground state densities for some V prime. Okay, so your space has to open up greatly, and then a lot of work since showing what is known as non-V representable densities. Okay, so we go on here, and now it's the constraint search formulation, which generalized. Also, Hohenberg-Kohn had the restriction to that you had non-degenerate ground state. Not only had to be ground state, but a non-degenerate ground state. And so in 1979, I wrote down an F of rho of this form, plugged it into here, and shows you get E ground state. Now put it explicitly later. This was influenced by some statements and the formulas that were put down by Perkis and Lieb in 1983, earlier actually, but this is the most accessible one, but it was after mine in 82, put it down too, and this is called either the Levy functional or Levy-Lieb. Now, I assumed there's always the infimum that you could write it down as, and but Lieb showed that there's an actual minimizing wave function. You should actually first write this as an infimum, which is the lowest value of the integral of the wave function that yields the density. That's the value of the integral, but it doesn't necessarily, and that's valid, of course, and all this is valid. Okay, you write this as an infimum, it's the lowest value of integral. But then the question is do you get a minimizing wave function? And Lieb showed that there is a minimizing wave function. Again, it's always valid that you will get a minimizing expectation value here, but not necessarily that there's a minimizing wave function that does it. And Lieb showed the minimized wave function. And that's why I feel it's nice to call this Levy-Lieb. There's something on the web where people ask if Levy did it first, and Lieb asked, why is it called Levy-Lieb? And there are all kinds of answers. It's been going around for 10 years. But no one gives this answer. And I think this is the answer that Lieb showed, that there is a minimizing wave function. The difference between an infimum and, for students here, and where you can have infimum, not a minimum, you'll have the infimum. Let's just say you're doing energy of the ground state of an atom, and you keep lowering the nuclear charge, a 2-electron atom, let's say. And then as Z goes to 0, okay, as Z gets smaller and smaller, you're always going to find you're going to have a minimizing energy, and eventually it becomes a 1-electron energy. But you don't have a minimizing wave function. The other electron just drifts off. So you have an infimum, the energy of a 1-electron wave function, but no minimum there. Okay, so now here's the constrained surge proof. You take E ground state, you're minimizing the expectation value of overall psi, and then you break it up into inner and outer minimization. For a given rho, you minimize all psi's that give the rho, and then you minimize over all rho. So the minimum over rho is broken up into 2 steps. But all psi's that give a given rho give the same expectation value with respect to the external potential, V. So this is the one here. And the minimum of rho here is min psi yield rho here. And this is F of rho. So this is for degenerate as well as non-degenerate. This expanded the, as I said before, the original Hohenberg-Kohn functional quite easily. And this is the proof that I think if you give it to a bunch of people and give them a week, that they'll come up with. Okay. It says, V representability is not required. It could be generated, and you don't need that V prime. And this constrained proof was what Kohn called the Levy-Lieb functional and proof, and this is the one that he published in his Nobel lecture. Not his original proof. He used this proof here, which was more general, which was I was very happy to see. Okay, so what was done? Okay. So as started by Hohenberg and Kohn and continued, as we see here, through the work of Elie Lieb and I, you establish the existence of an F of rho to play with. Okay? You have exact definitions. And you have the definitions, but the definitions in the theorem doesn't just justify the use of F, it gives you the instructions. It's a prescription. It says, let's have functional such that it has the properties of doing this constrained search, or the original Hohenberg-Kohn form. The functional should do it. It should do it. You want to just have the density, but it should do it. So we're not just saying F exists, hey, you're allowed to do it, but the definitions that I just put up shows you how to get at it. Okay? That's the important thing. So exact constraints, and then you get exact, accurate, approximate functionals. We've done very well. The functionals, we have PBE, Li-Yang par, scan. Minnesota uses, for instance, more of the you know, the less of the explicit constraints, and of course we have the machine learning, and all used, and like machine learning with constraints helps out there, etc. But you have to always look at the definition. You always have to look at the definition. Okay, so here is the first clear use of the exact definition here, and it's this here, or f of rho is the min, or f of rho is this f of rho psi min rho t plus v, which is greater than, so any wave function that yields rho, because of, by the definition of f of rho, any wave function, expectation value of t plus v has to be greater than or equal to f of rho, okay? So when you're deriving properties, a lot of the properties are derived in this way. You have this here, and it's greater than or equal to this here. And you have all different kinds of properties, and you have scaling. I'll talk on Monday, I mentioned Heinz and Lieb-Oxford bounds. You have a large number of constraints. One constraint is you have, when the density is uniform, you should get the, you know, the local density approximation results. And so there are many, the ionization energy constraints that are used by people like Roy Beer and Leo Kronig. You assume that the highest occupied orbital energy is the, in your calculation, is the same as the ionization energies. And I'll talk about this tomorrow a little bit. Okay, so that's, we go. So let's partition F. So what we're going to do now is take a drink of water, and we'll partition F, and then we'll look at the pieces of F, okay, in terms of the rigorous definitions, okay? Okay, so here we have the partition of F. F is the minimum Masayos rho of T plus VE psi, okay? And F of rho is Ts, okay? The cone-sham non-interacting kinetic energy, the classical Hartree energy that exists in Thomas Fermi's theory, the exchange energy and the correlation energy, and this is U rho here, that was here. Okay, we have this partitioning, and then what we do is this constrained search here is broken up into different constrained searches here, okay? So what time do I have to, the ends at what time, 10:45? Okay, so that's good. All right, so let's start dealing with the different parts. The non-interacting connect. And Whit, is he here? You're here, right? You'll be talking in a couple hours about TS, right? Okay. All right. So what about the scaling of TS? I hope you mentioned the scaling, how it's scaled. Great, okay, I'll do it right here. Okay, okay. So here we go right here. We have the density here, like this, and uniform coordinate scaling for TS. All right, so because in TS, the cone-sham kinetic energy, the constrained search involves just one operator here. The coordinate scaling is simple. When the coordinate scaling, when the constrained search involves just one operator, the coordinate scaling is always very simple. So it is with the cone-sham kinetic, and there's another place where it's very simple, and that's in the functional, the first order density matrix. because there you're minimizing the expectation value of just the repulsion energy, right, of the wave function or ensemble that yields the first order density matrix. And therefore, that has very simple scaling, okay? And then we'll see how scaling, knowing the scaling, leads to having knowledge of the structure, or some knowledge of the, or key knowledge of the structure. Okay, so let's look here at the kinetic. Here, you could see the slide, okay? Yeah? Good? Yeah? I can't see that well, but that's okay. So what is it? It's the TS is the minimum of all wave functions that yield the density of psi t plus c psi, okay? And that's the same as the Cone-Sham kinetic energy here. Now, T has, we know what the operator involved in T, of course, it used del I squared, so it's a second derivative, okay? So the magic number is 2, okay? So we have two things going on. It's a constrained search involving just one operator T, and we have the magic number 2 here. And when you do the scaling, you have Ts rho equal lambda squared, okay? The 2 is because you have a second derivative. So look at what the definition does. It says you look at the constraint search, but you also look at the operator. So the functional has to take into consideration what your operator is. The operator is the kinetic, second derivative, okay? And since it involves a constraint search of just one operator T, it's simple scaling, and since it's the kinetic operator 2, it's lambda squared 2. Okay. So let's give an example. Let's say you're just starting out, trying to derive Thomas Fermi theory, you have the plane waves, you have a beginning student, all right? What does the Thomas Fermi kinetic energy look like? What is the, not the prefactor, but what is the form? Within 5 minutes, we know what it is, right? And what it is, you go here, we use this here, right? It has this form, right? And now we end up with the integral of rho to the 5/3. And how do you get that? You get, it turns out, you have three-dimensional space, 3 here, and the 2 is that lambda squared. So you get the 5/3. You could actually work it through within 2 minutes, but that's what it turns out to be. So people see it right away. Okay? So this is the power of coordinate scaling. You see, immediately we see that this could be the only form. And we'll see later with exchange, also you have one operator involved, and what you're going to have is 1, because the repulsion is Rij to the 1 power, right? Plus 3, three-dimensional space, over 3, 4/3. Just like this, right off the bat. Okay, so here we go. And let's now go to the exchange. Remember, F is Ts, right, plus U, that we know, plus exchange correlation. So let's go to now exchange, and it's the Cone-Sham wave function, or the wave function that minimizes. Cone-Sham is the wave function that yields rho and minimizes just one operator. So since it's minimizing just one operator, it minimizes just one operator, that means it's going to be simple scaling, okay? And it minimizes, the Cone-Sham, it's not minimizing anything to do with VE, but it minimizes one operator. But then you take you're using VE in here, minimizes one operator using VE in here, and you see the Rij to the -1 power, so the magic is 1, okay? So there's, with the scaling, you have Ex exchange, rho lambda, lambda Ex, and this was all this scale, beginning scaling stew was in a paper with John Perdue and in 1985, okay? Okay, so let's move on. Now let's give example. Local density approximation. This is the Dirac exchange, right, form, right, that we had, who Heinz talked about. And so we have, it has simple scaling lambda, and then the Ex local density approximation, or the Dirac form, is the integral of rho to the 4/3. So 3, again, three-dimensional space, or 1 now, and you get 4/3. You just work it out. That's what happened. And it was just a few steps. And you'll see that's what it is. So it's giving really a lot of information right off the bat. Okay, now let's get to this. Okay, again, in the paper with John Perdue here. Correlation. This is the toughie. Why is correlation tough? Kinetic is not, exchange is not, but why is correlation tough? Why is that? Why is that more complicated? How many operators involved in correlation? Remember, all. You're using T plus VE. They have two different homogeneous operators, T and V. Two operators involved in the definition of correlation. So it's a whole big ball game with a lot of different differences. Okay, so this is counterintuitive because if you didn't, you're going to get an inequality, but it's counterintuitive because if you don't look at the definition, you would get equality, okay? I'll tell you the story of equality. Before people looked at the definition and used scaling, they were getting equalities in the correlation, and equalities all over the place. And so you really have to look at it. And earlier papers all had the equalities until 1985. And when I was as excited about this upon seeing this as the constraint search when I saw that. Because I saw, wait, you have an inequality. I only seeing equalities. So by the time Par-Yang book came out, these are earlier books that I had. Martin, I'll show the books on Tuesday. And the book by Dreisler and Gross, we got it right. And then for some reason that I cannot understand, there's a later book, Engel and Dreisler. Do you know that book, Engel and Density Functional Theory, Engel and Dreisler? The same Dreisler, written years later, he put equality. I don't know what happened. How do you get it right and not? I don't know. But they corrected it. That's a good book, and later, so if you have an earlier edition of Engel and Dreisler, you have the equality, not the. So what's this? This is a fundamental. It's counterintuitive, meaning if you don't look at the definition rigorously, you're going to get it wrong. Okay, so this is it. The counter-uniform coordinates, counterintuitive, but it's not counterintuitive if you use the definition. Okay, while if I take psi rho min, the wave function that minimizes t plus v, and I scale it, okay, this scale wave function, of course, yields the scale density, but does not minimize t plus v, all right? This is it. If you just take a wave function, you define that yields the density and minimize the expectation value of t plus VE, okay? And then you would think you would just scale that wave function, and that would be the proper wave function to be used for the functional exact expression for the functional for the scale density. But that is not true, because the scaled wave function is not the one that minimizes t plus v, even though it gives the scale density. So you get an inequality. And this inequality is the fundamental inequality for a bunch of large number of scaling constraints that are used in the functionals, such as PBE, scan, etc. Okay, and even Lie par and other functionals around. Okay, so it's this inequality. Okay, so let's go on and see what's happening. Having that inequality says that this is here, right, that when you, let's just go back for a second. So when you scale and you have the kinetic operator here, this brings out a lambda squared, because kinetic is second derivative v rij to the minus 1 power. So the key point, get a lambda squared and a lambda. All right, so now what you all get is this, what you're getting is that lambda squared t, the kinetic of the original density, lambda, the repulsion of the original, is greater than, for lambda not equal to 1, psi rho lambda min, here, or it's greater than f of rho. So this is another way of putting the basic inequality that is used to derive correlation energy constraints. Again, it comes from the definition of the functional that is valid, shows that you, by variational principle, is valid. So one quick thing that we got was this here, this inequality here. All right? This inequality here. And that's what we get basic. And then you start getting more. And work with Andy Gerling, further work with John Perdue. We get uniform scale. Yes, what?
Can I ask something? Can you go back one slide?
Sure.
This inequality at the bottom, right?
Right.
Why is lambda constrained to be larger than 1? Also, if it's less than 1,
No. Oh, wait. Let me just say this. Yeah. This to this required a lot of steps. I have to show you the steps. It's not this, clear this. I'll have to show you the steps, okay? So it's deceiving the way I put it up. Thanks for asking the question, okay? Okay, yeah. Good question. But then you get something like this. The uniform scaling constraint at high and low densities, you get that out here. As lambda goes to infinity, the correlation energy is bounded, less than minus infinity. And in fact, it's a second order perturbation energy. It's not big at all. This is a very important result. And at small lambda, it goes linear lambda. So from that relationship, you play around and you get all of this. It requires a lot of steps here was involved in this. And there's an interesting story here. You have, for the uniform electron gas, at high density, you have the Gell-Mann-Bruckner result. And the Gell-Mann-Bruckner result says that as lambda goes to infinity, as uniform, there's no lambda, it's an infinite gas uniform, as the gas becomes more and more infinite, the correlation energy goes logarithmically to infinity. It's not bounded, okay? Not bounded, okay? But what we have is, for any finite system, you take a density and you get lambda going to infinity, so it goes delta-like. EC goes, the correlation energy goes to a constant, But in fact, we know what it is. It's a second order energy, like Muller-Lipset, second order perturbation theory. It's not a very large energy. In other words, the density is pretty, for a molecule, let's say, pretty insensitive to this scaling. So if you impose this condition, that it goes to second order like, and certainly less than minus infinity there, then you correct for the overbinding that the local density approximation had. So all the great GGAs, that's what they were doing. And they were correcting for the fact that the LDAs, the original calculations, were overbinding. There's an interesting story about that, because what happened was certain simple LDA calculations were getting, bindings, or inert gas bindings, and they were considering it a success. But the reason it was a success is because LDA used to overbind things. So when it took the inert gases, they were getting bindings, so they were screaming success for the wrong reason. Okay? All right. So anyway, that's that here. And so it's less than minus 50. I should dedicate this part of the program to my 4.5-year-old granddaughter with affinity. Hopefully she'll be sitting here, maybe as a mathematician. She asked my daughter, do numbers ever stop? So my daughter says her answer. She gives her whole lecture, and she talks about infinity. So my granddaughter's probably thinking, well, it stops. It goes to something called infinity. So anyway, all right. So let's move on here. And here, the scaling here of, you see for the first order density matrix, right? Okay. So we have two things going on here. We have the repulsion operator, 1 over I minus Rj, right, to the 1 power. So that's the key 1. But also the constraint search is just 1 operator, simple scaling. So for the first order density matrix theory, we have this relationship here. Okay, and this is the scaling relationship as gamma is scaled. So this is the constraint search. Gilbert put it down earlier, and then I put it down as a constraint search, and then Steve Alone. I went to Steve Alone and I said, hey, he had done work with the what is this? Oh yeah, then Steve Alone put it down as an ensemble constraint search. Okay. You talked about it yesterday, man. Pure state and ensemble. So there's an ensemble constraint. So it's nice. So it means first order density matrix theory is nice because you're putting more information into the function. Therefore, you could get a lot more out of it. Okay, as was pointed out earlier. It has simple scaling, so right off the bat, you can construct it to satisfy the key scaling constraint. But of course, by the fact that it has fewer scaling constraints could be a disadvantage because there's less stuff to put in with the density. So it works both ways. I don't know which is better, but you could look at it. It works both ways. All right, so that's it. And I have a review, if you want, back in '95. It doesn't contain the new stuff, but a lot of the old stuff is in there. Okay, so now let's go to the second part of the talk in 15 minutes. We have a scaling of spin density separately, and we have this paper by this character, Karen Burke and friends here. And so we have this paper. It's really the first one that started looking at what happens if you scale one of the spin densities. Okay, one of the density is the sum of spin densities, and they have an exchange relation here, and then they postulated, I like conjectured, based on physical reason and the numbers they've seen, the following, that if you scale just one density to 0 here in the functional of the correlation energy and keep the other spin density fixed, is you get the same result of just the correlation energy of just the down density, you see? I don't know if you can read this that well. So this is it here, so that is it true that if you scale to 0 one of the spin densities up and you keep down fixed is the same as having no up spin density and just a down spin DC. And at the time this was published, my former graduate student Federico Zaharev was a postdoc, and then he left afterwards. And then we started thinking about this for years and years. Once in a while we get together. In other words, not continue, whenever we would get together. And then we thought maybe you could use non-uniform scaling. I haven't shown any of that, and that could be used. But then eventually we shall prove it. We shall show you could get scaling. And why is scaling relations difficult to get for scaling just one spin density? Your wave function that contains spin, space and spin, is anti-symmetric. So which coordinates, what do? You scale coordinates. The electrons are indistinguishable. So what we realize is, from seeing other work stimulated by an expansion, first by McQueenie and then Felipe and Umarga, they have an expansion, and they were able to prove that you could use constrained searches in spin density functional theory using spin-free wave functions. Okay, so this is it. So density and spin density through spin-free wave functions. This over here is the spin density functional theory. And if you have a spin-dependent potential up and down here, you have the spin density up and down. And of course, you need spin density functional theories if you have, like through magnetism, V up and V down. So you have this, and this is our normal rho here. Density is the sum of the spin density, and you have this here. And so what we're going to show is that this F, you could use spin-free wave function number 1, and 2, through these spin-free wave functions, you could derive constraints when you scale just one spin density. All right, so we go like this here. Motivation for the use of spin-free wave functions, as I just said, it is difficult to derive key coordinate scaling constraints for F, the spin density universal functional for the purpose of it, for the use of wave, because electrons are indistinguishable, as I said before, specifically if you just want to scale one of the spin densities. I mean, if you scale both of them with the same scale factor, you have the same result as before. You're just scaling the density. But we just want to scale. Okay, so conventional definition of F is, well, this is conventional constrained search definition. You're minimizing psi yields rho up, rho down. X is space spin, right? And that gives psi min here, where psi is anti-symmetric with respect to spin interchange space of any two electrons, where up is this and down is this, the standard definition of spin densities. All right? And now we have spin-free definition. In this paper, this was an unpublished, submitted to Physical Review A 2 weeks ago. All right, it was submitted 2 weeks ago to Physical Review. In this paper, we established that this F, the spin density F, you're allowed to use spin-free wave functions. And that's this here, that F is the minimum size, where these are just space, functions of space. And if they're M up electrons, it turns out the size is antisymmetric in the first M, and separately antisymmetric in the last N coordinates. Further spin densities are given this way. You do this integration or all, and you leave out 1, and then you all, and you leave out 2 to, from M plus. So, but you're doing it over space. That's it. Okay? Is this clear? What is it? Okay. So what is the proof? Here is the proof, and this is where this is the expansion of McQueenie and Ummergraf and co-workers. You could always expand a spin density wave function in this way here, where these are the spin functions here, and the G's, I's are space functions here. And of course, because this is antisymmetric, these are all equivalent, meaning they're the same except for the, interchanging the electrons, etc., and a possible change in sign. But notice the following, that since the whole wave function is antisymmetric here, that I said 2 up, 1 down. If alpha here in this case, 1 and 2, these have the same spin. That means R1 and R2, G3 is antisymmetric with respect to the interchanging R1 and R2, you see. That's it. So that's what I said. In the first M is antisymmetric, in the last M minus 1 is separately antisymmetric, and we have this. And the same thing here, like this. So they are equivalent. And I use the word in quote equivalent. They're not equal, equivalent. You're going to see the expectation values are the same. Okay, so now let's go to the next slide and just take any expectation value in the constrained search. And you see that since the spin functions in here, these spin functions are all orthonormal. Okay, and so the cross terms vanish. So you go like this here, and you have 3 times this, but it's the same square root of 3 in terms of any of the GIs here, and that's the same as a psi involving just space. So it follows, you go from here to here, you start with spin, you get without spin, thus there exists a psi with spins that has the same expectation as given one without spins as one with spins. Further could be shown that psi without the spin has the same set of spin densities as those with the spin. But of course, you get at them the same spin density, but you get at them differently. Here, you just using spin-free wave functions to get the spin, but here you use the spin wave functions. But the same spin density, same values. Okay, that's the proof. And similarly, we go the opposite direction. We could start with the spin-free wave function, add a single product of the spin functions, anti-symmetrize, okay? And what happens is you get the same result. You go from spin-free and you get the same T plus VE with a spin, and therefore, since you go in both directions, it means the minimums are the same, and therefore F could be spin density F for spin density functional theory, or you take out the spin-dependent V's and you have regular density functional theory. You use spin-free wave function in definition. And by the way, most of the time we use upspin and downspin for calculations where we don't have spin-dependent potentials. So this is used generally. Spin density F is used all the time, okay? Even when you have no spin in the, it's more common than okay. So this is the case, and that's what we desire. So you could use spin-free wave function here, okay? So now we could scale this animal here because, you see, we've gotten rid of the spins, okay? So the use of spin-free enables derivative of constraints on F for the purpose of approximating it, okay? And the examples follow. So you have the basic inequality. So here, what we're doing is just scaling the upspin. So you do that, but putting just the scale factor in front of the coordinates R1 to Rm, you see. You can work with spin-free wave functions, you see. And you get the fundamental inequality, and that leads to various relationships, for instance, this one involving F. And we somehow have some powerful relationships that have never been used because they've never been derived. You see, this is the first time these derivatives, this is work submitted 2 weeks ago. And so we have this. Now, what about the conjecture of Karen Burke and co-workers that stimulated our thinking about all this? It's from a derived spin from identification. It can be shown that F row down, row up, this is inequality here, and psi min lambda, and it's B lambda psi, where B is an operator. So you do have an equality provided that the operator is not your ordinary, you could show it's not the ordinary T plus VE, but you have the lambdas in here. You could show that here, and you have an operator B, and then you go and look at what happens. So let's say, remember, the question was, if you let lambda go to 0, do you get the same result as if you take this all out and put a 0 here and you just have the F of just the spin down density? Well, let's look at what happens here. When lambda goes to 0, this disappears in the operator. Lambda goes to 0, this becomes this becomes 0 here, so this is infinite. It's an infinite separation, so that all expectations go to 0. So this, you get rid of this, you get rid of this here, this goes to 0, so you just have this, and this is then just the Hamiltonian of the spin-down electrons. And as a result, you have for the whole F as F rho, you have rho up lambda here, here gives this result. If this goes to 0, as we just showed, because B lambda, it just becomes the T plus VE of just the downspin, and you get this. So because we're purely downspin T for n minus 1 electrons. But and then you could do the same for the other parts of F, and as a result you have this, which was previously postulated, as we say, or conjecture. So we derived the result. And we derived the result by realizing that you could use spin-free wave functions in the definitions. That it's also for, do I have a few minutes to write? Yeah? Also for density functional theory, because this was spin density, but of course f of rho is equal to, of course, is the same thing as f of rho up, f of rho down, where rho equal rho up plus rho down, right? Yeah? Okay? You agree? So what we have is a spin-free formulation of density functional theory. Instead of using wave functions with spin, we could use wave functions without spin. Okay. So now, how about this? Rho is rho up plus rho down. What about this? So therefore you have rho, and you scale rho, right? I'm scaling rho. I'll scale. I'll use the scale factor up here. All right, that's a scaled rho. And then this is equal to f of rho lambda up plus f of rho up down. Okay, so there is, I wish I brought the paper. Wait, scale up and down f of rho scale. Is this true? We have this, and I have this. Is this true? Well, but if I say this is true, well, let me just say something. Hold on. Ah, no, I was wrong. I lied. I lied. How did I lie? Was this true always? No. F of rho is the min, okay, of rho up, rho down, f of rho up, rho down, and where rho equal rho up plus rho down. You see, you're searching over all spin densities with all different ups and downs. 3 up, 7 downs. 5 up, 5 down. So this is it here, you see? So this is the relationship, you see? So we're all, rho is rho up and down, rho down, f of rho, that's f of rho. So that's it, okay? All right. So therefore, it's not always true that f of rho lambda is less than or equal to f of rho down. See, because you have to do this search, you see? It's a little tricky, okay. Now, one of the things I'm pointing out a little more to what was done in Heinz's talk, we're using the Lieb, if the density matrix. So if you have F gamma, okay, the density matrix, and then you start off with the Hartree-Fock form, right, where you're allowed fractional occupation numbers, okay? Okay, because of that inequality in Lieb's paper, and then you have an E correction. So this is a correction, or you can call it correlation gamma. What happens is that, remember, F this is just the repulsion operator, or this is just, F is VEE, just VEE in that theory here. So this is the same as VEE gamma equal F of gamma, okay? That's it. So what we're going to have to do, then if you scale, gamma scale, as I put it there, okay, so, okay, is equal to F Hartree-Fock gamma scaled plus E correction gamma scale. Okay, but since this can only go up with fractional occupation of the correction of gamma must be negative. It's less than or equal to 0. And also, this scales, both these scale just as lambda because it's a simple constrained search. And we know the correction, we know what this exact. This we know exactly. And we do know that E correction from what I've been saying with scaling, and we scale this, is equal to lambda E correction gamma, okay? That's it. So it's kind of nice. We know exactly how the correction scale. So unless there is any correction to my talk, it's over. Thank you. Yes.
It actually relates to the last part. So I understand in what you showed us, the VEE is just Coulomb repulsion between the electrons.
Correct. Right. Yeah. Right.
Because I'm asking because at about the same time where Kiron was formulating the conjecture that you are now proving, Kajik and I were working on density functionals for neutral fermionic atoms, and the interaction was just a dipole-dipole interaction.
Okay.
Which is very different from the Coulomb repulsion. Okay, it's explicitly spin dependent. Okay, so I'm wondering
whether you could use that in any way.
This carries over because in that formulation you naturally have to distinguish between spin up and spin down components.
Well, let's see. Okay,
field.
let me see your work, and I'll look at it. Well, maybe we could do something with that.
There's a variation of this.
Yeah, that would be great. That would be fantastic. Yeah, maybe we could do it. Yes. Wait. You were first. Yeah, maybe in relation to this. Yes. You have a question? Yeah, a comment.
It's in fact related to what Berger was saying. Is there a room for applied to neutral atoms, to electrons in the atom? Is there a room for the spin orbit coupling in your schemes?
Okay. Yeah, I mean, I have to think about that a little bit. Actually, yeah. So it's this is the lowest state of the situation that I defined. So beyond that, I really have to do some thinking. Okay, so this is the problem. Yeah. Okay. Any other? You had one, Karen. Yeah.
Well, I was going to say.
I mean, you have to think about all this also in relation to all the stuff that Paul Ayers talked about, right? You have to be a little careful with things, but I think we're okay. Yes.
So in response to what you were saying, I believe almost all these results, or essentially all of them, rely on the coordinate scaling of the Coulomb interaction.
Right.
Which may not be,
Yeah.
may be different. However, right, in simple limits, like say the high density limit where correlation is weak, then even a more complicated interaction, you can apply the same results. So that's where you look when the interaction is more complicated. And the other thing I wanted to say is that,
Well, wait a second. Hold on. Wait. You mean like in the low density, it's the Wigner, yeah, and high density is that. In fact, the low density is more of the problem in the high density. I should say something interesting. Yeah. Okay. So we're gonna. So what's the question?
Well, I was going to make a comment about this postulated thing. That, well, certainly at the time we ended up with a postulate because we had no idea how to prove it. We tried and we gave up. So I'm very glad to see that.
Okay.
But also I think, while that's an interesting result, and I think it's important in some contexts, right? I think the machinery that we've developed for answering this problem is very powerful. The
Okay.
spin-free wave function.
Yeah. Okay. Yeah. Thank you.
Used in lots of
Yeah, that's what we would hope. We would hope. Yeah. It's more general than that. Yes. Right. Okay. Great. Well, let me tell you something about high density. This is kind of interesting. When we in that slide, if I get back to it, I have to get back to this slide here. This is back. Back is this. It is labeled nicely because you go really way back. Here, this is the one, is it? Yeah. So I put it up at an APS meeting, and this one here, that it goes to a constant. This is the one, because it's not true with a uniform gas. The Gell-Mann-Bruckner result, uniform gas goes logarithmically to infinity, the correlation energy. So it seems to violate that, but of course that's a different situation. It's infinite. Walter Cohen in the back of the room says, he says, Mel, I don't like this stuff. It's an APS meeting, American Physical Society meeting in Seattle, where I first had Starbucks coffee. So he says, I don't like it. It was a crowd. It was in the back of the room. He was standing in the back. Small room, so it was crowded, but it was in the back. So he says, I don't like it. I don't like it. And I explained it's a different situation. With Gell-Mann-Bruckner, you have infinite gas. And here I have a finite number of electrons, and I'm scaling, so it just goes like a delta function, for instance, in an atom, so it's different. I don't like, and he liked it later. He liked it later, but not at that moment. A few months later, so it violates Gell-Mann-Bruckner. A few months later, I get a phone call. You all know Michelle now. Most of you, I hope, have had the pleasure of meeting you. And they live in Santa Fe. They lived in Santa Fe. So Michelle's mother calls up, and she says, Mel, do you know Murray Gell-Mann? I played tennis with his wife. So they became very good friends, Michelle's parents and the Gell-Manns. If you know anything about the personality of Murray Gell-Mann, it was very similar to Michelle's father. They all got along. But I regret that I never, and then we spoke about their relationship, and they became very good friends. And I never went out and visited during that time, but I should have sent him the papers. I don't, he did the work at one time, and I should have showed the difference. But I didn't, and never thought of it. Because I know he went on to other things, of course. Eightfold Ways was way before his other work, but so that was an interesting story. Yeah. All right, thank you very much. Well, I don't know, who's the chair? I am. So what's left of a coffee break, whenever there's some coffee break? Okay. Okay.